Well, all right, it's time for us to do some more practice. And our problems right now are going to be all about absolute max and absolute min, which is good. We can be focused and disciplined. And it's important that we do the practice because that's how we grow as mathematicians and as problem solvers. And so do as much as you can on your own. As you're watching the video, if you haven't done the problem yet, make frequent use of that pause button. Get to a certain point and be like, okay, let me see if I can keep going by myself. Because that's what you want to get to the point where you are confident in how you can do math. All right, well, we'll get there by starting to do the practice. So let's begin. For our first problem, find the absolute max and absolute min of the function 1 minus the absolute value of x squared minus 5x minus 6 plus x. Now, at first glance, we might say, well, what can we do? Well, so what we need to do is think about, first off, does this have an absolute max and min? And I think we can say pretty quickly, yes. We see it's on a closed and bounded interval. We're going between 0 and 7. We're including the endpoints. And the function that we're considering is a continuous function. Now, you might say, what about the absolute value? Well, the absolute value is always continuous because it has that nice V shape. And if I put a continuous function like a polynomial into a continuous function, the result is still continuous. So it's a continuous function, closed bounded interval. It will have an absolute max or min. All right, so our goal is, how do we find it? Well, we know the process. We're going to be making a list, then we're going to check it twice. All right, so we start with the list. What are the lists? The critical points. So for our list, we're going to have a couple of points. First off, you always throw in the boundary because they're always going to be on the list, and it just feels good to make progress. So put those points in. Those are kind of our freebies, 0 and 7. Now, to go forward, we have to start thinking, hey, how do we handle something like absolute value of x squared minus 5x minus 6? Okay, so let's take a couple minutes to figure out how we can think about this function. Really, the problem is we don't like having absolute value in our function. So we want to get rid of the absolute value as best we can. So let's start by understanding the function x squared minus 5x minus 6. Now, this function, it actually is kind of nice. It factors. This will factor as x minus 6 times x plus 1. Because you want two things that multiply to negative 6, add to negative 5. And if you're not certain, just carry it out, right? X squared, then plus x minus 6x minus 5x, and minus 6. Now, in terms of the picture, we know it's going to be a parabola that opens up. The up is because the coefficient of x squared is positive. We can also see, because we factored, we know where it's going to hit the x-axis, so we know where the x-intercepts are. They're going to happen at negative 1 and at positive 6. So that we have this parabola that's doing something. All right, so that's x squared minus 5x minus 6. Now, what happens if we look at the function absolute value of x squared minus 5x minus 6? Well, the answer is where it's positive, and when I say it, the original function, nothing happens. So the parts that are above the x-axis are still going to be above the x-axis. The parts that is below the x-axis is where you flip. And so you get that shape. So it's going to go something along that line. You can see here, it looks like we have a bit of a happening. All right, so now we can say, aha, we can think of this in terms of pieces. We can say it has one behavior below negative 1, another behavior between negative 1 and 6, and another behavior above 6. So we really don't care about what happens below negative 1 because we don't even care what happens below 0. In particular, if you think about our function, we really only care about what's happening to this part of the function between 0 and 7. So here's our idea. We're going to get rid of the absolute value by turning our function into a piecewise function. So we're going to rewrite our function, f of x. It's going to be two things. Well, if we are, say, let's do from 6 to 7 first. From 6 to 7, notice the absolute value of x squared minus 5x minus 6 does nothing. And so it would become 1 minus x squared minus 5x minus 6 plus x, and that's for 6 less than or equal to x less than or equal to 7. When we're between 0 and 6, the absolute value does have an effect. So it changes the sign. Now notice we are originally subtracting here, so if we change the sign, it'll turn it into a 1 plus x squared minus 5x minus 6 plus x. And that's for 0 less than or equal to x less than or equal to 6. So we'll clean it up just a tad. So if we group things, so that's x squared minus 5x plus x makes minus 4x plus 1 minus 6 makes minus 5. And that's for between 0 and 6. And here we'll have minus x squared minus minus, that's a plus, so plus 5x plus another x is plus 6x. Then 1 minus minus 6, that's 1 plus 6, so that'll become plus 7. And that's for 6 less than or equal to x less than or equal to 7. All right, so there's our function, and now we have it in a nice broken down manner where our pieces are nice polynomials. And so we're like, much better. At least, if nothing else, much easier to work with. We like things which are easier to work with. Okay, now, what comes next? Well, we've already put in our endpoints, so everything else deals with the derivative. So let's do the derivative. Now, if our function is piecewise, our derivative is piecewise. So, f prime of x. Well, just take the derivative of each piece. 2x minus 4, and that will be for 0 less than or equal to x less than or equal to 6, and minus 2x plus 6, and that'll be 4, 6 less than or equal to x less than or equal to 7. Okay, I've told a small little lie. Can you see my little lie? Okay, my little lie is I should not have put less than or equal to on these places. The reason I shouldn't have put less than or equal to on these places is because whenever I'm gluing functions together, I have to be careful because normally there's a little bit of kind of action going on there where there's a sharp bend. All right, so I'm going to step back and say, well, let me not include 6 yet. So the way I check is I look and say, what would happen if I plug 6 in? Well, here I'd get 2 times 6 minus 4 is 8. Here I'd get negative 2 times 6 is negative 12, plus 6 is negative 6. Well, they're not equal, which means that you really do have a sharp bend at that point. In particular, that means the derivative is undefined at 6. Well, any place where the derivative is undefined, that makes our list. And therefore, 6 has made our list. Congratulations. All right, so again, the first two are boundary. Now the next one is undefined. Okay, what comes next? Where does the derivative equal 0? Good question. Now let's go piece by piece. So let's start with this part. When does 2x minus 4 equal 0? Well, that's not so hard. 2x minus 4 equals 0 at x equals 2. All right, that should make our list, right? Yeah, it should, because that's between 0 and 7. So, yes, fantastic. All right, how about negative 2x plus 6? When does that equal 0? Well, that equals 0 at 3. All right, and does that make the list? It doesn't. It doesn't go on the list. Now you're probably like, whoa, Steve, hold on. Slow down. when we were making our list, we had to find all the places between 0 and 7, and 3 is certainly between 0 and 7, so why are you saying 3 doesn't go onto the list? Here's why I'm saying it. Notice that I'm only looking between 6 and 7. So x equals 3 is not in this range. In other words, it's not in this, let's not use range, let's say interval. So when I'm looking at this x equals 3, 3 doesn't go between 6 and 7. So the fact that x equals 3 is a place where this derivative equals 0 doesn't matter, because the derivative for 3 is up here. So it's outside of consideration. So this is one of those things where you're like paying attention, like, okay, yes, this is a place where the derivative equals 0, but it doesn't matter, because it's really a place that I should be looking. Now, would you have lost anything by adding too much to your list? No, not really. It really just meant extra work. But of course, you could have a mean test writer who's like, you shouldn't have put that on there. That's not a critical point. Well, of course, you need a mean math teacher? Why, I never have heard of such a thing. All right. So we are now done with making our list. And so we found our boundary points where our derivative is undefined and where our derivative is 0. Okay, so the process now says take your list and plug it into the function. So we're going to plug every one of these points into our function. So we're going to plug 0, 7, 6, and 2, all into the function. Now, some of these things are easier to plug in. So for example, when you plug in 0, it's fairly straightforward. In fact, we can just come in here. At 0, you'd have 0, 0, negative 5. Oh, that was quick. So when you plug in 0, you get negative 5. Now how about for 7? Well, we might have to work on that one. So let's see, what do we have here? So here is our function at 7, so we're going to use our second rule here. 7 squared is 49. That's being subtracted. 6 times 7 is 42, plus 7 is 49. Negative 49 plus 49, they exactly cancel out. So the function at 7 is 0. Okay, that's nice. Now, the function at 6. Okay, now here's kind of a fun thing. You could come here, or you could come there, right? Because these are both variations of how to define the function. And the nice thing is, we know that x squared minus 5x minus 6 is going to be 0 when we plug in 6, because that's where we hit the axis over here. So what you end up with is 1 plus 6, which means that when you plug 6 in, you'll get 7. If you don't believe it here, you can go through and do the work. Negative 36, positive 36, plus 7, you get 0. All right, last thing, plug in 2. So here we go. We're going to get 4, 2 squared, because remember, this is our 2. 2 is between 0 and 6. So 4 minus 8 minus 5. So if you take 4 minus 8, that's negative 4. Subtract 5 more, gets us to negative 9. All right. Now we scan our list and we say, what is our largest value? So between negative 5, 0, 7, and 9, our largest value is 7. All right. So this is going to be our absolute max. And what's our smallest value? Our smallest value is negative 9. And so this is our absolute min. All right, we found it. Good, good. So yeah, this is by the way, a very common strategy. When you have absolute values involved, they don't really work well with doing derivatives. So it's best to break things up into pieces such that each one is reasonable to work with. All right, well, that's a good warm-up. A couple more to go. So let's do another problem. All right, next problem. Find the absolute minimum and absolute maximum of the function g of t, which is t minus 3 e to the t minus 3 halves times t minus 4, where we're going between 1 and 3. Now this is kind of interesting because this is not a polynomial. this is a function which involves an exponential as well. So it's going to be a little bit different. We're going to have to figure out how this works. Well, but that's all right. We like a challenge. Okay, so let's work our way through this. Now, first off, these functions are very nice. They're all continuous functions. So we notice a continuous function. Our interval from 1 to 3, closed bounded interval. So we know there is an absolute max and an absolute min. So, woohoo, good for us. Now we actually have to find it. Well, so we do our process. Our process is always going to be the same when we're looking for absolute max and absolute min. We start with the list. Throw in the endpoints, 1 and 3. Now, for the rest of it, we're going to focus on the derivative. So here, we just have to work through. There's no real surprises. So, let's see. I think before I take the derivative, I might expand this last part. So this would be t minus 3. This is just the function. I'm not taking derivative yet. Minus, this would be 3 halves t squared. Right, 3 halves times t times t. And then minus makes a plus. And 3 halves times 4 would be a 6 times t. Okay, so let's see. What do we have? So g prime of t. Take the product rule. Get rid of the first. I'm thinking of t minus 3 as being the first function. Get rid of the first is 1 times the second plus the first, t minus 3, times the derivative of the second, which is e to the t. Then here, 3 halves t squared, the 2 comes down, so it'll become minus 3t. And then here, plus 6, because the derivative of 6t is 6. Well, interesting. One thing we can see right away is that the derivative is never undefined, because these are nice functions. They're always defined for every value of t. So we've got to attack the problem. When does the derivative equal 0? And at first glance, it's not too promising, but we haven't cleaned up yet. So if we've lived a good, clean algebra life, hopefully something nice should happen. Well, notice that these first two terms both have e to the t. So let's factor the e to the t out. And if we do that, what will we have? Well, we'll have 1 and a t minus 3. So if we put those together, that'll be t minus 2, which is t minus 3 plus 1. Now here, in the second term, I say, well, let's try to make it look like t minus 2. Can we do that? Well, if we pull out a negative 3, we would have t from the first term, and then the 6, pull out negative 3, is minus 2. Wow, they set it up nicely for us. Okay, see, now you have a t minus 2 is common to both of those pieces. So that can come out. So we have t minus 2, and then that's times by e to the t minus 3. All right, good. We've made good progress. All right, well, now what comes next? Well, when does this equal 0? So this will equal 0 when t is equal to 2, or when e to the t is equal to 3. So t equals 2, that's between 1 and 3. That makes the list. All right, how about e to the t equals 3? Well, let's bring down the t. How do you get the t outside of that exponential? By taking a log. So you would get t equals natural log of 3. Now, do we know anything about natural log of 3? Well, if we think about e to the t, so e to the 1 would be 2.718, because that's what e is. So if I want to get to 3, since 2.7 is below 3, I have to go above 1, but not a lot above 1. So log 3 is a little bit above 1, but not by much. So that is certainly going to be between 1 and 3, so that makes the list. Okay, good. We're done. We've made our list. Now, what comes next? Well, now we need to evaluate. Okay, so let's plug these in and to our function and see what we can say. Now, some points I suspect are going to be a lot easier for us to plug in than other points, but, well, we'll figure it out. And worst case scenario, we just grab a calculator. And I know it's not the worst thing, right, in the world. So, are there any that are easy? Well, I think 3 should be pretty straightforward, right? Because what happens when you plug in 3? 3 minus 3 is 0. So that term goes away. Then you have minus 3 halves times 3 minus 4. So, all right, let's make some notes here. All right, so g of 3 will be 0 times e to the 3, then minus 3 halves times 3 times negative 1. Well, the minus makes a plus. 3 halves times 3 is 9 halves. Okay, so g of 3, is 9 halves. We can even say that's about 4.5. When we plug in 1, what do we get? Well, we're going to get minus 2 times e, then minus 3 halves times 1 times negative 3. Right? Because we can see how those numbers go in. Okay, good. Well, 3 halves times 1 times negative 3. Well, this is again, it's 9 halves. But now you subtract 2e. So 9 halves minus 2e. Okay, so we'll say that's 4.5 minus 2e. Well, we certainly know which one of these is bigger. Okay, how about 2? What happens when we plug in 2? So, g of 2 is 2 minus 3 is a minus 1 times e. So minus e, and then minus, we have 3 halves times 2 times minus 2. So minus here makes a plus, and then we can cancel the 2, so we get 6 minus e. So that's 6 minus e. Okay, good. All right, we're making good progress. Whoops. E squared, right? Because it's e to the t. In this case, t was 2. All right, now log 3. Well, g of log 3, that would be log 3 minus 3 times e to the log 3. Well, we know that's 3. Then minus, that would be 3 halves times 3 minus 4. Well, 3 minus 4 is, this is negative 1. Oops, I plugged in 3. It's log 3. So minus 3 halves log of 3 times log of 3 minus 4, which is some crazy number. Okay, so we get 3 times log of 3 minus 3, and then minus 3 halves log of 3 times log of 3 minus 4. All right, now, at this point, you're probably saying, what do you do? Well, we have to figure out which one is larger and which one is smaller. So, I would say, this is a fair time to use the calculator. So I'm going to go and grab those numbers really quickly. All right, we'll be back in just a second. And we're back. Okay, so I went and I asked my calculator, and I have some data. So let's start with the easy one. 4.5 is approximately 4.5. Well, you kind of knew that one. All right, 4.5 subtract 2e. Well, because e is 2.71828, it's about 4.5 minus 5.4. So roughly around negative 0.9, right? Well, we can do a little bit better, negative 0.936. Now, log 3 is close to 1 because the number 3 is close to the number e, 2.71828. And so they're not very far apart from each other. And so it shouldn't surprise you that g of log 3 is not very far from g of 1. It turns out it's approximately negative 0.922. Now the last thing, 6 minus e squared, well, that's approximately negative 1.389. All right. Now you might be wondering, what if we didn't have a calculator? Well, then you'd have to be very patient and get some approximations for e, like 2.71, and work with that. And there are ways to get approximations for log 3 as well. In the old days, meaning back 30, 40 years ago, what would you do? Well, you'd have a book full of data, and you'd say, hey, I need to know what is this number approximately, and you'd go look it up in the book, and the book would say, hey, that number is approximately this. You'd say, oh, okay, great, good, glad to know that. And so that's what you would do. Now, we're not done. The last thing to do is to scan. What's the largest value? Well, between these four options, the largest value is 4.5. So our absolute max is 4.5. Okay, what's the lowest number? Well, between, again, these four options, it's this negative 1.389. So our absolute min is 6 minus e squared. So in this case, we see that the absolute max will occur at a boundary point, and the absolute min occurred somewhere in the middle. See, that can happen. It's perfectly okay if that happens with functions. You know, you never know. You do the work, and then you see what turns out to be true. All right, well, good. A little bit more challenging. I tend to avoid problems that require going and grabbing a calculator. So I guess we'll throw in a 1 once in a while, right? Keep ourselves a little bit honest. All right, on to the next problem. And our next problem will involve an absolute max and absolute min. Who would have guessed? All right, come on. Here we go. Find the absolute max and absolute min for the function 12x to the 1/3 minus 3x to the 4/3, where we go between negative 1 and 2. And it says, on a side note, this is what f of 2 is. Okay, somebody was nice and they said ahead of time, you might need to know this value. Now, is this function defined between negative 1 and 2? In particular, you might get nervous when you see like these fractional exponents and you see negative numbers. Well, as long as in your exponents the denominators are odd, negatives are perfectly fine. No worries. It's when you have like a negative to a half power, square root of a negative. That's bad. But this is no problem. We can work with this. All right, well, let's begin. These functions it's fine, it's continuous, nice closed boundary interval. So we start by making our list. Throw in our endpoints, 1 and 2. Now, next step, take our derivative. So our function, I'll write it down for easy reference, 12x to the 1/3 minus 3x to the 4/3. So the derivative does what? Well, the 1/3 comes down. That'll be 4x to the minus 2/3. Here, the 4/3 comes down. 3 times 4/3 is 4x to the plus 1/3. Well, we want to clean this up. So they both have a 4. We'll factor that out. They both involve powers of x. So we pull out the lower power. In our case, it's the negative 2/3 is the lower power. So pull that out. 4x to the minus 2/3. And then we'll have what? We'll have 1, because we grabbed everything, minus, and here the power will be 1/3, subtract what you pulled out. 1/3 subtract negative 2/3 gets us to 3/3, which is just x. All right, so there's our derivative. Now, we're after two questions. Is our derivative ever undefined? The answer is yes. We can see, because of that negative exponent, we're undefined at x equals 0. Okay, so that means what? 0 made our list. Now, the function is perfectly fine at 0 because we have 0 to positive exponents. That we can live with. It's the derivative that has the negative exponent, and that has the problem. Now, is the derivative ever equal to 0? Well, yes. We can see our derivative is equal to 0 at x equals 1 because we'll get a 0 entry here. So, what does that say? Well, that says 1 made our list. Now, you might say, hey, 1 was already on a list, but that was a typo because what should it have been? It should have been a a negative 1, right? Ha ha ha. Double check. Double check. Okay, so there we go. There's our list. All right, good for us. We found all our points. Now, the next step is to plug it in. So we're going to plug all these points in. All right. Some of these will be simpler than others. So for instance, looking at this, I can think I could do f of 0. That's pretty easy because anytime you have 0 to a power, that's 0. So f of 0 is 0. Also, I could do f of 2. I can see that's approximately 7.559. Now, if you're wondering how I did that so quickly, I'm just reading that off. Okay, how about f of 1? Well, 1 works really nicely because 1 to any power is going to be 1. So it's looking at the coefficients. You get 12 minus 3, which is 9. Now, negative 1. All right. The cubed root of negative 1 is negative 1. So negative 1 to the 1/3 will be a negative 1. What about negative 1 to the 4/3? Well, you can say, well, take the cubed root of negative 1 is negative 1, but then you raise that to the 4th power, it's a positive 1. So you'll end up a negative coming from there and a positive from there. So it's going to be minus 12 minus 3, which makes this a minus 15. All right? So that's what happens when we plug in negative 1. Very negative, very negative. Okay, but now we're ready to answer the question because we're after the absolute max and absolute min. So we scan our list and we say, all right, where's the largest number? And it's there, it's 9. So this is our absolute max. The largest possible output for the function, given it goes between negative 1 and 2, is 9. The smallest is here. So the absolute min is going to be negative 15. All right, well, we found them. There you go. Good. After the last problem, this is kind of easy. Well, but of course, the last problem was extra spicy. We like it when things are fun. All right. One more problem. Find the absolute maximum and absolute minimum for the function f of x is a half times x squared minus arctangent of x squared minus 1, where we go between negative 2 and positive 2. And there's a note, arctangent of 3 is approximately 5/4. All right, well, that's nice to know. Okay, well, let's see what happens. I somehow suspect that we'll need to know arctangent of 3. But let's not just sort of jump the gun and throw it in there. Let's sort of develop it in a sort of more systematic, natural way. So we know we're after the absolute max and absolute min. So when we see any problem that asks for absolute max or min, we say, okay, this is make a list problem. So we make our list. And we say, what goes on our list? The endpoints always go on our list. So our endpoints are negative 2 and positive 2. Well, now we start saying, all right, the rest of it comes from the derivative. So we take our derivative, f prime of x. Derivative of 1/2 x squared would be, the 2 comes down, and so 1/2 times 2 is just 1. We're left with x. It's not so bad. Now, how about arctangent of x squared minus 1? I suspect this one's going to be more interesting. So this will be minus. Now for arctangent, you take 1 plus whatever's on the inside squared. Okay, so 1 plus the inside squared times by the chain rule, the root of the inside. Derivative of x squared minus 1 is 2x. All right, good, good. Progress. All right, well, what can we do now? Well, one thing we can do is say, hey, they both involve x. We can factor that out. So we have x, and then we have 1 minus 2 over 1 plus x squared minus 1 squared. All right. Now, is this derivative ever undefined? You might be a little bit worried because we do have a denominator. Can your denominator ever be 0? Well, it's 1 plus a square. A square can never be 0. So no, our denominator will never be 0. So that's good news for us. All right, so it's never undefined. All right, we can see, by the way, that x equals 0 will produce the derivative of 0. So that means that 0 has made our list. But now we start to ponder, could there be another point? Well, we got to start digging and see what we find. All right, well, so the last thing is we got to sort of explore this piece over here. So let's think about what that needs to be true. So in order for this to be 0, we need 2 over 1 plus x squared minus 1 quantity squared to equal 1, because that needs to cancel with that, right? So if we multiply through, we'll have 2 has to equal 1 plus x squared minus 1 squared. All right, and well, that's really 1 plus x to the 4th minus 2x squared plus 1, because we can square out x squared minus 1 squared. You know, you square the first term, minus 2 times the cross, so that's minus 2x squared plus 1. Okay, and that equals 2. Now notice what happens. All of your constants go away. Nice. Woohoo! So we're left with 0 is equal to x to the 4th minus 2x squared. Or we could say 0 equals x squared times x squared minus 2. And then we say, well, that tells us that x equals 0 should be on the list, and it already is. So 0 is like extra special. It shows up a couple of times. And when x squared minus 2 equals 0. So that says we need x squared to equal 2, or x should be plus or minus root 2. Now, which one of these makes the list? Does plus root 2, minus root 2, neither or both? And the answer is they both make the list, because we're going between negative 2 and positive 2. And square root of 2 is between negative 2 and positive 2, as is negative square root of 2. All right, so they're both on our list. Okay, it's kind of a very 2-y list. You know, we have plus 2, minus 2, plus root 2, minus root 2. Okay, and that's our list. Good, we've made our list. What comes next? Well, the next thing is we plug all these points into our function. So we're going to now plug every single one of these points into our function and see what happens. Well, I have to think about this for a little bit. Now, well, let's start with 0. Now, 0, what happens? You get 1/2 0 squared, well, that goes away, minus arctangent of minus 1. Now, arctangent is an odd function. So, what does that mean? Well, minus arctangent of minus 1, I can pull that minus out so that the two minuses cancel. It's really the same as arctangent of 1, which is pi over 4. Okay, so pi over 4. Good. All right. So at 0 we have pi over 4. Now, let's try 2. Let's try 2. 1/2 times 2 squared. 1/2 times 4. So that would be 2 minus arctangent of 2 squared minus 1, which is arctangent of 3. So that would be what's happened when we plug in 2. Now, we can actually save ourselves a little bit of work if we pause for a second. What do you notice about this function? Everywhere we see an x, it's really x squared, which means whether you plug in a positive value or the corresponding negative value, really the process will be the same. In particular, this function is what we call even. So if 2 minus arctangent of 3 is what we get when we plug in 2, it's also what we get when we plug in negative 2. So 2 minus arctangent of 3. All right. Well, now we need to plug in root 2. Well, what is that going to give us? Root 2 squared would be 2 times a half would be 1. Then minus arctangent of root 2 squared is 2 minus 1. So 1 minus arctangent of 1. Well, that's going to give us 1 minus pi over 4. So 1 subtract pi over 4. And that's the same as what happens when we plug in negative root 2. All right. Well, we're in good shape, actually. We're in pretty good shape. So, arctangent of 3 is about 5/4. So what can we say? Well, 2 minus arctangent of 3, and this approximation is actually a pretty good approximation. So this is really close to 3/4. So this is very close to 3/4. So now we have our various numbers. 3/4, pi/4, 1 minus pi/4. Well, pi/4, pi is a little bit bigger than 3. So pi/4 is larger than 3/4. 1 minus pi/4, this is going to be below 1/4 because pi/4 is bigger than 3/4. So 1 subtract pi/4 would be smaller than 1 subtract 3/4. So really, when we compare these, pi/4, this is the largest. So the absolute max is equal to pi over 4. And then 1 minus pi/4 is smaller than 3/4, so our absolute min is equal to 1 minus pi over 4. And notice our absolute min occurred at 2 places. It's okay for it to occur multiple times. No problem. No problem. But there we go. There's the answer. And hey, wow, we were able to find it. That's great. I like it when we can find an answer. All right, well, these problems can be a little bit non-trivial, but you just work it through. Be careful. Take your time. Make a list. Be careful with your derivative. Figure out where it's undefined or 0. And then once you have your list, carefully evaluate. And once you get the hang of it, it's not so bad. It's just making sure you do all the steps. So, well, that comes with practice. So keep doing the practice. And hope you have a great day. Bye.